In this video, we'll be talking about how to combine matrices when we can add them, subtract them, and multiply them. Let's get started. So what do we mean when we say we'd like to add or subtract two matrices? Well, first of all, by definition, we're saying we would like to combine the entries which are in the exact same location by adding or subtracting them. In order for that to be possible, they must have the same size. So first of all, we have to check whether or not it is even possible to add our two matrices. Once we've determined if it is possible, we'll begin the adding and subtracting process. The second thing we're going to be looking at in this slide is what do we mean by scalar multiplication? Well, that sounds like you're multiplying a matrix by a scalar, which is another word for a constant, a number that will scale up or scale down your values inside your matrix. So for example, if you see the number 2 in front of a matrix A, that's literally saying that you want to multiply every entry of matrix A by the number 2, doubling each entry in the matrix, basically. Okay, so we can scale up or down. So let's take a look at this example. We're given a matrix which has 2 rows and 2 columns. So remember, that means that is a 2 by 2 matrix. That's the size of it. And its rows are 2, 5, 7, negative 1. We're given matrix B, which is also 2 by 2, with rows 3, 6, and 9, 4. We're given matrix C, which has 2 rows and 3 columns. So that's right, that's a 2 by 3 matrix, with rows 1, 2, 3, and 4, 5, 6. And we're given matrix D, which has, can you see it? That's right, we have 3 rows and 2 columns. So this would be a 3 by 2 matrix. So when asking you in the following 2 steps here, could you take A and subtract twice B? And then could you take 3 times C and add it to D? You first have to decide whether or not it's even possible. So let's talk about A and B. Well, A is a 2 by 2. B is also a 2 by 2. And if you're wondering, well, wait a second, what happens when I multiply matrix B by the number or the scalar of 2? Well, that will just double the entry sizes, right? It won't actually change how many rows or columns you have. So it turns out for this first instruction, we are able to do this matrix subtraction. So we'd start with matrix A, the 2 by 2 matrix with row 2, 5 and row 7, negative 1. And then we would subtract the result of 2 times matrix B. So looking at matrix B, we're now just going to double the entries of matrix B. So go ahead and do that on your own. Feel free to pause the video and come back to see how you did. Okay, so 2 times 3 was 6, 2 times 6 was 12, 2 times 9 was 18, and 2 times 4 was 8. So now I have one 2 by 2 matrix minus another 2 by 2 matrix. In order to do this matrix subtraction, we simply will subtract our entries that are in the exact same location to produce another 2 by 2 matrix. So let's take a look at our answers. You can try it on your own and then see what your answer is. Okay, so we did 2 minus 6, which was negative 4 for entry 1, 1. We did 5 minus 12, which was negative 7 for entry 1, 2. We did 7 minus 18, which was negative 11 for entry 2, 1. And we did negative 1 minus 8, which is really negative 9 for entry 2, 2. So we have our new matrix is a 2 by 2 matrix that resulted from taking matrix A and subtracting the matrix we got when we doubled the entries of matrix B. So that is an example of matrix subtraction. Notice matrix addition would have worked exactly the same, only we would have added those entries instead of subtracting them. Okay, what about the next one? Is it possible to triple the entries of matrix C, so 3C, and add that to matrix D? Well, tripling the entries of matrix C is certainly possible. We would simply have 3, 6, 9 for row 1, and 12, 15, 18 for row 2. Definitely possible. So this part we could do, no problem. What size matrix is that? Well, it's still 2 rows by 3 columns. But what about matrix D? It's still 3 rows by 2 columns. And as we mentioned earlier, by definition, in order to add or subtract 2 matrices, they better be exactly the same size. So since these are not the same size, we cannot do this addition. It is not possible. So sometimes when you're given problems on homework or tests, and they ask you to add or subtract matrices, they'll always ask you to do it if possible. So sometimes it will not be possible, and that was because those matrices were not the same size. So definitionally, they wouldn't be able to be done. Okay, well, let's go ahead and talk on our next slide about another important matrix operation. Let's take a look. Another important matrix algebra operation will be to solve a matrix equation. Now, right now, this is definitely in the abstract situation. We haven't actually given you any applications yet. But in our next video, we'll be talking about how to apply matrix algebra to a system of linear equations. So I promise this does have meaning, but right now we're dealing in the abstract. So when we're asking you to solve an abstract matrix equation, typically what that will look like is something like the one below here, where we have 3 times matrix X plus 2 times matrix A is supposed to equal matrix B. Now, to solve an equation, if this wasn't a matrix equation, but just a nice little algebra equation, and it's linear in nature, you would normally just try to isolate the variable X, wouldn't you? Exactly. Similarly, if you were trying to solve this matrix equation for matrix X, our variable matrix, you would begin by trying to isolate 3x, right? So to do that, you would notice that I would need to undo matrix addition. And the good news is the opposite, or the inverse, that undoes matrix addition is still matrix subtraction, just like you would with a normal equation. Addition undoes subtraction and vice versa. Okay, that won't hold true for multiplication later on. Okay, we won't have something called matrix division. That doesn't exist. But for addition, we can use subtraction. So if we were to subtract 2a, matrix 2a on both sides, where the order is very important, okay, we would get that 3x, 3 times matrix X, should equal matrix B minus twice matrix A. Okay. Well, is that even possible? There's no need to go further if it's not possible to do that much. So let's think this one through. Matrix B was given to us as a matrix with 2 rows and 3 columns. So that's a 2 by 3 matrix. So was matrix A. So it turns out that I am able to subtract matrix B with twice matrix A because they're the same dimensions, same rows, same columns. So this part is feasible, so we can continue. The next step normally would be to undo scalar multiplication. And scalar multiplication can be undone with scalar division. Now, notice I said scalar multiplication, not matrix multiplication. We'll talk more about that coming soon. So I can undo scalar multiplication with scalar division. In other words, I can divide both sides by 3 or multiply both sides by 1/3. So if I did that here, multiplying both sides by 1/3, I would take the result of that matrix difference and I would multiply it by 1/3. So let's see what this would look like. Now I would get X by itself on the left, and I would have 1/3 of the result of taking matrix B, which I'll just copy it here. Matrix B was 2, 1, negative 3 for row 1, and 4, 0, 5 for row 2. And now I'm going to be subtracting twice matrix A. So what was twice matrix A? You can try that on your own. That's right, it's going to be 2, 6, 4, negative 10, 8, and 0 when you double those entries. Remember how to do the matrix subtraction? We did it on the last slide. Feel free to pause it and do it yourself. Okay, let's see what we got. We got 1/3 times this new matrix after subtracting the 2, where the first entry would be 2 minus 2, or 0. So we got that first entry right. The next entry would be 1 minus 6, or negative 5, followed by negative 3 minus 4, which is negative 7. Good job. And then 4 minus negative 10, which is really 4 plus 10, would give me 14. Then we'd have 0 minus 8, which is negative 8. And we'd have 5 minus 0, which is 5. So if you told me that the answer is 1/3 times this matrix, 0, negative 5, negative 7 for row 1, 14, negative 8, 5 for row 2, you would technically be correct. However, in the back of a textbook, if you were trying to check your answers, you probably wouldn't see that because they would expect their students to know how to multiply a matrix by a number or a scalar. To perform scalar multiplication means to multiply every entry by that scalar. So this would become 1/3 times every entry, or 0, -5/3, -7/3, +14/3, -8/3, and +5/3. So this would be the matrix X, which would make the original equation true on both sides. Meaning that if I were to go back to the original here to check my work, you could do that by hand or using technology. You could triple the entries of this matrix, add those entries to the entries of 2A, and the result should be the entries of B. Okay, so you could check step by step, is this truly the matrix that makes this equation true? Again, on the bottom of that slide, it tells you that later on we'll have matrix equations in the next video, in the next section, which in fact involve undoing matrix multiplication. But since we do not have matrix division, we'll have to use something called a to the -1, read as a inverse. So we'll be talking more about that next time. Okay, so let's go ahead and head over to our next slide where we talk about what is matrix multiplication. So first of all, remember what we've done so far. We know how to add and subtract matrices as long as they have the exact same dimensions. That's right, the same number of rows and columns. It turns out that we're allowed to multiply two matrices as long as the inner orders are the same. Now, right now you have no idea what that means, and we're going to try to clarify that right now in context with an example. So let's suppose we have matrix A that has 2 rows and 2 columns. So it's a nice 2 by 2 matrix with row 1, 2, 3, and row 2, 4, 7. And we have matrix B provided for us with, again, 2 rows but 3 columns. So it's a nice 2 by 3 matrix. I always recommend to students to write down the size of the matrix to the bottom right of each matrix so that you can visualize what's going on. Now, if we were asked to add these matrices right now, hopefully your response would be, I can't. And not because you haven't practiced, but because you know the definition of addition of matrices, right? Addition and subtraction can only happen if the matrices are the same size. But it turns out that multiplication is possible if we wanted to multiply matrix A on the left by matrix B on the right. It is possible in that one particular case. And let's take a look at why that is by definition. If you notice here, for matrix A, the size of the matrix, it had 2 columns, didn't it? And matrix B similarly had 2 rows. We call those 2 numbers the inner order of the matrix product, right? So the inner order of the matrix product would be both 2's. As long as their inner orders are the same, it is possible to multiply these 2 matrices. Now on the bottom of the slide, I tell you, what about B times A? So if I switched the order, would the matrix product exist? And if you think about that, you would have a 3 by 2 times a 2 by 2. Well, what would the inner order be? If you had a 2 by 3 times a 2 by 2, a 2 by 3 times a 2 by 2. Feel free to write that down and think about it. What would the inner orders be? Well, one would be a 3 and the other would be a 2. So no, B times A does not even exist because the inner orders wouldn't match. Now, right now, that still probably sounds very confusing. So let me go ahead and show you how matrix multiplication works definitionally, and maybe that'll clarify this for you. So if I was trying to find the resulting product, A times B, in this situation, the first thing I would recommend is draw a template for what you're expecting to happen. We're expecting to have a matrix product that has an order or a size of the outer product. By outer product, I mean these numbers, the 2 for the number of rows of A and the 3 for the number of columns of B. That's called the outer order. So it turns out that the size of my resulting product when I multiply A times B should have 2 rows and 3 columns. So in my template, I'm going to show 2 rows with 3 columns. So 2 rows with 3 columns. So there's my template. It's ready to receive my entries. Now, if you remember from our previous discussions or previous videos, we discussed that the entry name usually has a subscript, and the first number is the row and the second number is the column. So for example, if we're trying to find the resulting product matrix, capital A times capital B, its entry in the top left corner would be entry 1, 1, because it's in the first row and the first column of that resulting matrix. So looking at that entry, defining it by its name, it would be little ab 1, 1. So what would that look like? Well, the reason the 1, 1 is helpful, I usually use my fingers to keep myself straight. I'll say I'm looking at the first row of A and the first column of B. So let's line those up. I'll even highlight them for you. The first row of A with the first column of B. So you can feel free to use colors when you're doing this or use your fingers to keep yourself organized, right? So for entry 1, 1, we're looking at the first row of A and the first column of B because of the order A times B. That's the order we're going. Now, how do we do this? We're going to multiply 2 by 1, so 2 times 1, and we're going to add the result of 3 times negative 3. So let's see if you followed what I did. I did this entry 2 with this entry 1. I did this entry 3 with this entry negative 3. I multiplied together and added. So this would become 2 minus 9, wouldn't it? In other words, that entry is a negative, that's right, negative 7. So I now know that entry 1, 1, the entry in the first row and first column of my product matrix, is a negative 7. Okay. Now I'm going to do this a few times, and then I would recommend you pause and try them yourself before I give you your answers. So let's take a look at our next entry, and I'll go ahead and erase what we did last time so we can see clearly what's going on this time. So let me get a new color for us so we can follow along, hopefully. We'll do brown if it works. Okay. So next entry we're looking at happens to be right there, which is in our first row, second column. That's right, first row, second column. So for entry 1, 2, first row, second column, I'll look at the first row of A with the second column of B. And let's see what happens in this situation. We would have 2 times 3, that's right, and then we would have 3 times 0, and we'll add those two products together. What do we get? That's right, we get 6 plus 0. 6 plus 0 happens to be 6. Okay, so in this situation, we have the entry for the first row and the second column of 6. We'll do one more together, and then you can try the other 3 on your own, and I'll give you the answers if you want to pause. So let's take a look at our next entry for row 1, column 3. So to do row 1, column 3, let me erase my circles here so you can follow me, hopefully. We're in row 1 of A and column 3 of B. Okay, so let's see where that brings us. We would have 2 times 4, good job, plus 3 times, that's right, 5. That would produce the products of 8 and 15, which when we add 8 plus 15, what do we get? Good job, 23. So 23 is entry 1, 3 in the first row and the third column. All right. At this point, I recommend you pause and try to get the entries on the bottom row and see if you get to the same conclusion as I do. Okay, let's see how you did. For entry 2, 1, did you end up getting, get new colors here, negative 17 for this entry? In other words, you took the second row of A with the first column of B. That would be 4 plus negative 21, which gives you negative 17. For entry 2, 2, did you get 12? Good. For entry 2, 3, did you get, I believe, 51? When you did the first row of A with the third column of B, that would be 4 times 4, which is 16, plus 35. That is 51. Okay, so we now have found out how to get a matrix product A times B. Remember, it's only possible if the inner orders are the same and the outcome of the product should be the size of the outer order. In this case, 2 rows and 3 columns. So notice once again that it was not possible to do B times A in this case because they did not have the same inner orders. Okay, sometimes it will be possible, but not always, to do both. Well, let's have you try the next one. Feel free to pause and see how you did and then come back and check your results with me. Last example, here we go. In this example 1, it says, could you find A times B, but also B times A by hand, if possible? Now notice I'm saying by hand because there is technology that can do this for us, right? TI, 83, 84 calculators, all of those can do this for you. Symbolab, you'll notice my links in my notes, they all have it pre-done for you online. But keep in mind that the online or the interactive calculator apps, those only work if you have numbers as your entries. And when you get into a class called linear algebra, you won't necessarily have numerical entries. You'll have to be able to do this by hand. So it is important that you've at least had this foundation before you move on and then abandon it and use technology. Okay. So you're always welcome to check with technology, but you have to be able to demonstrate it by hand as well. So let's take a look here at A times B. We're given matrix A as a 2-row, 3-column matrix. In other words, 2 by 3. And we're given matrix B as a 3-row, 2-column, so 3 by 2 matrix. And we're asked to find the product matrix A times B and then B times A if possible. So looking at the first one, if matrix A is 2 by 3 and matrix B is 3 by 2, can we do that matrix product? Can we find that matrix product? Yeah, we can, can't we? Because their inner orders are the same. They're both 3. And the resulting matrix should be size 2 by 2, the outer order. So here's what I'm expecting. I'm expecting a matrix with 2 rows and 2 columns. So I make some room for my entries, okay? And let's see if we can get the same entries. Again, feel free to pause it. I really encourage you to try this on your own and then check your answers. All right, so for that first entry, right here in the top left corner, in row 1, column 1, I would be looking at row 1 of A with column 1 of B. Let's see what that would look like. I'd have -2 times -1 plus 1 times 2 plus 0 times 4. Let's see what that means. Well, we'd have 2 plus 2 plus nothing, which is 0. So the result there would just be that's right, a 4 for entry 1, 1. What about for entry 1, 2? We'll pick another color here. How about, yeah, sky blue is good. Let's do this entry here in row 1, column 2. So again, row 1 of A, but this time we're looking at column 2 of B. So that would mean in this situation, -2 times 5, which is -10, plus 1 times 3, which is 3, plus 0 times 0, which is 0, and -10 plus 3 is in fact -7. So that entry would be a -7. And similarly, you could do entry 2, 1 by looking at the second row of A with the first column of B, and eventually, hopefully, you will get, for these two, your solutions should be, let me find them here, 13 for entry 2, 1 in the second row, first column, and -12 for entry 2, 2. So try that on your own, see if you can handle that. Now let's talk about the second one. So that is the answer for A times B, a nice 2 by 2 matrix with row 4, -7 and row 13, -12. But what about B times A here? Let's see what would happen. Well, B again is a 3 by 2 matrix, and A was a 2 by 3 matrix. So can this matrix product even be found? Check your inner orders. They match, which means yes, we do have to do it, don't we? The size will be a 3 by 3. Good job. So we are expecting a bigger matrix this time with 3 rows and 3 columns to result. So I have my 3 rows with my 3 columns. Again, I'll do a few of these with you and then hopefully you can get the idea and try the rest on your own. So let's try the first one together. For this top left corner, entry 1, 1, I would be looking at the first row of B with the first column of A. Notice the order matters for matrix multiplication. So what we'd have there would be -1 times -2, which is 2, plus 5 times -3, which is -15. And that result, when you add 2 and -15, is -13, isn't it? So that would be my first entry in row 1, column 1. Similarly, if I went to find the next entry in row 1, column 2, entry 1, 2, I would be looking at the first row again of B, but this time the second column of A. And what would that be? Well, -1 times 1 is -1, plus 5 times 1 is 5. Did you get 4 for that entry? Good job if you did. We'll do one more entry together, and hopefully you can follow the process for the rest of these. And you're always welcome to contact me if you need more help. So in entry 1, 3, row 1, column 3, we're looking at row 1 of B, column 3 of A. What would that look like? Well, negative 1 times 0 is just 0. And 5 times 2 is just 10. So we, in fact, are getting a result there of 0 plus 10, which is 10. Okay, so in row 1 so far, we would have had negative 13, 4, and 10. Then if you were to continue, I won't do the rest of them with you, but I will tell you where to go from here. If you're trying to get this entry in row 2, column 1, you would look at row 2 of B with column 1 of A, which would have been negative 4 minus 9. And negative 4 minus 9 is negative 13 again. And the resulting entries for this matrix are going to be, after the negative 13 in row 2, you'll have 5 in column 2 there. You'll have 6 in column 3. In row 3, you'll end up with negative 8 for row 3, column 1. You'll end up with a 4 for row 3, column 2. And you'll end up with a 0 for row 3, column 3. So check those out yourself, and if you have any problems getting those, please make sure to contact me or check out the math centers for help. They're very good at this, and we're all here to help you. Okay, so at this point, here's what we've talked about. We now know how to add and subtract matrices, but they had to have exactly the same size, same rows and columns. We also know how to get the scalar multiplication of matrices by multiplying every entry by that number. And finally, we know how to multiply matrices as long as they have the same inner order. All right, so now it's up to you. Good luck practicing. I'll see you next time. Remember, math is not a spectator sport.